do you think we see around? Humans need light for the act of seeing to take place. Light comes to our eyes by reflecting from the object we want to see. So, how much do we know about light and speed? The speed of light, or photons, is 299,793,458 meters per second in a perfect vacuum. This equates to roughly 1,079,250,000 kilometers per hour. We see photons traveling at this speed because they have no mass. However, they have kinetic energy, but we'll get to that a little later. Einstein called the speed of light the speed limit of the universe. He claimed that going faster than light would violate the causality principle. The causality principle simply means that there's a relationship between a cause and its effect, also known as the cause-effect relationship. Disruption of the causal relationship causes logic errors. As an example of this, a bullet will come out of your gun, hitting the target, while you haven't pulled the trigger yet. So, exceeding the speed of light means violating some fundamental energy laws, but if this could be done, even time travel would be possible. Before we dive into that, we need to understand what the speed of light is, so we can clear up some misunderstandings about the universe's speed limit. Every particle in the universe, including photons, moves in a field we call the Higgs field. You can compare this to swimming in the water, or walking against the wind in strong wind. Just as it is difficult to move through water or against the wind, particles face difficulty passing through the Higgs field, and this causes them to have a mass. Different particles interact with the Higgs field at different intensities. This is why some objects are heavier and others lighter. Photons also pass through the Higgs field, but they never interact with it. They simply just go through it. What does this mean? Since photons do not interact with this field, there is nothing to slow them down. In other words, they move freely in space, unhindered. So the only limit seems to be their already existing constant velocity. This speed is the highest speed at which the photon and therefore any other particle can also exist. Because, being massless and without interacting with any mass-gaining field, you cannot accelerate to a higher speed in these universe's conditions. If it was possible, the photons could accelerate to that speed. Because there can be no more massive structure than massless, therefore, there cannot be a particle that is lighter than a photon and that we can imagine going faster. Our universe is limited at this speed. So no matter who or how high technology we develop, we will never reach this speed. The reason for this is very simple. We have mass. You can accelerate a massive object as you wish, but we must say that to reach c, celeritas is in Latin, velocity, you need infinite energy. We regret to say that there is limited energy in the universe. However, that doesn't mean we'll settle for 99% of c. We always add an extra bit of energy, bringing the velocity closer to c, but we are not able to reach it. This is what we witnessed the most, near the speed of light, at CERN, where we found the Higgs boson. In the collisions we performed by colliding two protons with each other at speeds of 299,792,447 meters per second, only 11 meters per second less than the speed of light, that is, by accelerating both protons in opposite directions to the same speed, the energy limited by Einstein's E equals mc squared range, we can obtain incredibly energetic particles. When the updates in the Large Hadron Collider are completed, the collision speed will be increased to 299,792,455 meters per second, that is, only 3 meters per second less than the speed of light, and the fastest protons on Earth so far will be obtained. However, we must add the almost parameter to it. After all, the proton is a relatively heavy particle to the electron around the atomic nucleus, of which it is 1,836 times as heavy. Even if we obtain the protons from electrons at higher energies, the energy required to accelerate the electrons to the same speeds would be 1 in 1,836 of the energy required to accelerate the protons to these speeds, so 0.054%. The ratio is clear. Masses, that is, energies. In other words, we can find the energy equivalent of a mass by multiplying the mass by the square of the speed of light, which is a very large number. This principle also works in atomic bombs. Very little matter, atomic-sized isotopes releases an incredible amount of energy. Let's get back to our topic. The expected speed is 299,792,457,9,964 meters per second. In other words, 99.9,999,998% of the speed of light. This speed is in a vacuum, that is, in a vacuum where there are no matter particles in principle. It is 3.6 millimeters per second slower than the speed of light. Of course, these are the results of our world with limited energy resources. What comes from the universe in this context, we don't know. But it seems certain that something is going on at higher energies from our electromagnetic accelerators. Outer space is full of collapsed stars, supernova or stellar remnants, and supermassive black holes. Particularly when it comes to active centers of large galaxies with supermassive black holes, magnetic fields are observed billions of times more than our Earth's magnetic field or Newton fields. Cosmic rays, high-energy particles, generally protons, are coming from every direction in space and are traversing the universe, making almost every machine we produce in the world smaller in our eyes. Yes, as we go up to higher energies, we come across fewer particles, but the highest energies are no longer measured in GeV. TeV, tera-electron-volt, is 1000 times GeV. Even PeV, peta-electron-volt, 1000 times TeV. Instead of all these numbers, we can say that we can increase all these energies only up to 10 billion GeV, and we are limited here. Here, the number is quite interesting, because the universe doesn't allow it to go above 40 or 50 billion GeV and stay in those energies. Where is the problem? Is not it? Believe it or not, no matter how high the energy your particle has, it has to pass through a bed of radiation left over from the Big Bang. This radiation has a temperature corresponding to 2725 Kelvin, or negative 270 degrees Celsius, which means it's too cold for us. If we calculate the average energy of each photon in space, we arrive at a very small energy of 0.00033 electron volts. A high energy and charged particle always has the possibility of interacting with a photon. This is the same probability that all interacting particles have. If E equals mc squared allows, there is a possibility that a new particle may be created. This means that in the race of protons and photons to the nearest galaxy, the photon will reach our Earth by a margin of only 2.2 microns. A micron is 1/1000th of a millimeter. As a result, all charged particles in the universe, every cosmic ray, every atomic nucleus, every proton are limited by the speed of light. In fact, due to the remnants of the Big Bang, it's not even exactly limited to the speed of light, but very close to the speed of light. Today, we talked to you about why we can't reach the speed of light. See you later.